Schwarzkopf.
All right, thank you very much. So I'll be talking about Conclave, and this is a preview of a talk that will happen at Eurosys in a few weeks. So there might be a few rough corners, but I'm happy to explain if you have any questions throughout or if there's anything unclear. So I come from a systems end of perhaps this workshop audience. So my research is in distributed systems, and this is a collaboration with folks at BU, including Mayank, who's here, but also Nikolai, Ben, Andre, and Aza. And what this is about is basically taking secure multi-party computation and applying it to larger data sets than it applies to today in a usable way that's easy for programmers to do. So the basic problem probably needs no further introduction for this audience. We have a setup where we have, for example, a government regulator or an industry body that's regulating an industry where there's competing players who have some data. For example, in a credit card setting, the regulator might be interested in figuring out whether a recent initiative against predatory lending has been effective without obviously getting the details of every bank's customer portfolio. And specifically, they might worry about or might be interested in finding out what is the average credit score in different geographic areas by zip code, grouped by zip code, for example. So the easy way of computing this is to just tell the banks, give us your data, give us your customer portfolios, and then we'll compute the credit scores by zip code, and we're done. And of course, for good reasons, this is not a particularly appealing plan. For example, the regulator might get broken into, and the customer data might get exfiltrated, or alternatively, the regulator might accidentally leak more information than the banks originally agreed to, and it might compute anything over that data. So the banks are unlikely to agree to a plan where they need to give all their very sensitive customer and credit score information to a regulator. So what we can do instead, of course, is use secure MPC, right? So that would be a good plan of doing this. And we would all agree on a query. The banks and the regulators together would agree on a query. For example, what is the average credit score grouped by zip code, computed over the credit portfolios at the banks and some demographic information by zip code that the regulator has. Now, the way this proceeds is everybody inputs their data into the secure MPC using some cryptographic primitive like secret sharing, and then we execute an MPC protocol and eventually produce output that is revealed to either all participants or perhaps only to the regulator. But the threat model here, just to nail it down for the rest of my talk, is there are different threat models that MPC systems target. For the rest of the talk, I will target a semi-honest threat model. So we are assuming that all participants faithfully execute the computation, but that they are perhaps curious and are monitoring the computation to learn information about other participants' data. In particular, a set of colluding adversaries can read network messages, can inspect memory and storage contents, and can observe the control flow of the computation, such as instruction pointers and memory access patterns. So this is a standard semi-honest MPC threat model. Okay, so now that we've got the threat model nailed down, the problem here is is that the data that we're computing this over can be pretty large, right? So if you're thinking of banks, they have thousands of customers with tens of thousands of credit cards, and if the credit scores are identified by social security numbers, as they are in the United States, then you can very easily end up with millions of social security numbers entering into this computation. And that is something that is actually quite difficult for MPC systems to accommodate right now, at least if you do it in a sort of straightforward, usable way where the regulator or the data analyst writing the query for the regulator just uses an MPC system off the shelf. And we actually did some sort of exploratory experiments to see just how well do existing systems scale. And in this benchmark here, we're just looking at an aggregation. So we're just looking at a single operator that's computing a sum. On the x-axis, we have the number of input records into the computation on a log base 10 scale. So it grows pretty quickly. And on the y-axis, we have runtime of running that sum over this many records. And of course, less is better. So we looked at two systems specifically, a secret sharing based system, ShareMind, and a gobbled circuit based system, Oblivious C. And this is what we found for this operator. So you can see that Oblivious C sort of, it scales up to about 200, 300 records with negligible execution time, and then its execution time grows very, very rapidly. In fact, if we set ourselves a goal of answering queries like this within 10 minutes, then at even 1,000 records, Oblivious C is already out of the graph. Yes, please. The aggregation function is sum in this case. Sum with a group by, I should say, not just a straightforward sum, but sum with a group by zip code. So in relational terms, this would be a select sum over column group by the zip code column. Great question. So yeah, you need to sort because otherwise you can't group. Yes.
But that's the expensive part, not the sum part.
Not the sum. No, not the additions. The sorting required for the grouping and the equality comparisons between pairs, so that you find the group boundaries. That's the expensive part. All right. So Oblivious C, not so great in terms of scalability to a large input data. ShareMind, which secret sharing framework with very, very good performance. In general, actually gets a little bit further. It gets to sort of 20,000 and then goes through the roof. But all of this pales, I'll get to you in a second, all of this pales in comparison to insecure computation. Specifically, we just run this job on a sort of Spark cluster, copy all the data in and run an insecure computation. Then we end up with this curve where basically the data growth is not even making a noticeable difference to the runtime. Now, of course, this is insecure, so it's undesirable. But there's a huge gap between the scalability of secure computation and insecure computation. Yes?
Are those secure computation protocols malicious secure or
no, semi-honest okay. Security. Yes? So if I heard correctly, you asked, are we making the best use of existing approaches? So, how far did we push the optimization?
Yes. Yeah.
Okay, so the answer is we tried as much as we could within the realms of these existing frameworks to make the best use of the frameworks that we could. But of course, we did not hand roll our own MPC protocol from the ground up, right? And you might be able to get a little bit more if you do this. So we used the implementation languages that these frameworks like Obliv-C and ShareMind offer to implement the computation. Yes.
Did you find what was the was it algorithmic in their implementation, or was it like some other implementation itself? Like you ran like
right. Yeah, so we tried to best of our ability to find the bottlenecks and exclude implementation bottlenecks. For example, ShareMind has a sort of key value store that's implemented using a slightly arcane database technology, and that doesn't scale very well to large amounts of data. So we try to exclude that as much as possible by in introducing the data directly, by sort of trying to really nail it down. We believe that it is really down to the algorithmic complexity of the underlying operation. But ShareMind is a commercial product, so it's a little hard to tell because there's a limit to how deep we can go. But we did ask them, and this matches with the performance curves that they get. So. Yeah, so I'll get to the fundamental underlying limitations in 2 slides' time. So if I'll just continue and show you. Yes, one more question.
How is it possible that insecure is slower than the secure version?
Spark is using the JVM and has a pretty high startup overhead independent of the data size. So it's a sort of a 50-second overhead to starting a Spark job because it's designed for very large scale computation. But this is not fundamental. If you just wrote a Python program, it would be at 0 there. Okay, so we also looked at a join operator, which joins 2 relations by a key column. So it's a lot of equality comparisons required, and this is what we end up with. Pretty much the same picture. Oblivious C gets to sort of a few hundred records, and ShareMind gets to just over 1,000 before the curve starts looking a little unexciting. So what are the underlying fundamental reasons? That was one of the questions that we had here, and we sort of did think about this. What are fundamental limitations to scaling secure multi-party computation to large amounts of records? And one that's familiar to everybody is we have to do oblivious control flow. So whenever we need to access, sort of do random access into something, into a collection, we actually have to scan the whole collection so that the access pattern doesn't reveal anything. So that excludes things like efficiently branching on secret values. It also means that we can't index or cache very well. And that's sort of fundamental to what we're trying to do here. So an array lookup with a secret index, for example, is order of n, because we have to look at all the entries in the array. And then the MPC techniques themselves actually have overheads also, and this is sort of what you were getting at. So first, in secret sharing, when you do multiplication, you have to do communication over the network. So this is a non-linear operation. Just doing a multiplication is very expensive, while pure addition in secret sharing is quite cheap. And then with garbled circuits frameworks like Oblivious C, the problem with scaling to large data is that when each bit in the circuit has a label, it actually creates a state size blow up, right? So when normally you have 1 bit of input data, now you have to store a label that's more than 1 bit, depends on the security parameter exactly how big the label is. Then you're blowing up your input data size quite significantly, and therefore the circuit size, therefore the memory requirements, therefore computation time. So all of those things, they're fundamental, and Conclave sort of realizes that it has to work with these constraints. But what we can do, of course, is try and be smarter about how we use these oblivious MPC operations and only really use them when it's strictly necessary. And specifically, the problem that Conclave addresses is that an out-of-the-box MPC experience doesn't really provide you with that. For sure, it doesn't provide us with the scale that we need, but it also doesn't provide users with the ability to easily realize which operations specifically need to be secure. And no doubt these frameworks do give you the tools to implement such things. For example, you can decide which operations should be secure, which variables need to be kept private, and so on. But it is quite a burden on the user to figure this out, because if they're a data analyst who's not particularly familiar with MPC, then just the cognitive burden of understanding what actually needs to be kept private is quite high. And then that's not even to speak of the burden of implementing this, right? So the key idea behind Conclave is that in many queries, only some of the work actually must happen under MPC, and we can, using a query compiler, which is what Conclave is, we can help users by automatically deciding which parts of the computation need to be secured. And of course, in some sense, this is a normal query optimization problem, trying to execute a query as fast as possible, but now with a different set of constraints to what a query optimizer normally has. Specifically, we still need to maintain end-to-end security guarantees that the user originally specified or requested in their computation, and we better make sure that all of our optimizations match those guarantees. Plus, we want to reduce runtime, right? And sometimes this involves counterintuitive from a query optimization point of view trade-offs, like you might need to do more work in order to get lower overall runtime, which is not how traditional query optimizers think about things. So the key contributions that make this happen are we compile queries, relational queries, think of SQL or think of language-integrated query interfaces, to efficient, secure multi-party computation. And specifically, we have automated analyses in Conclave that minimize the amount of work that happens under MPC, that happens under the guarantees of MPC and using oblivious operations automatically. And furthermore, not just do we remove things from the secure computation that don't need to be computed securely, we also introduce new hybrid protocols which allow expensive operators in an MPC, such as a join or an aggregation, to be catalyzed by some computation that happens outside of the MPC, and that takes a lot of the expensive work away from the multi-party computation. I'll get into the details of exactly what trade-offs that involves, but think of it as we can accelerate joins by doing work outside of the secure realm and doing some work inside the secure realm. And we implemented a prototype that generates code for Spark and ShareMind, and also partially for Oblivious C, and we ran a performance evaluation on several realistic real-world queries. So the overall workflow of a conclave computation is as follows. The users and the parties participating all agree on a query that they wish to execute. They all run an endpoint to secure multi-party computation framework. And then Conclave takes the query, which is pre-agreed, and the schema of the data, which is also pre-agreed between the parties, and turns that through query compilation into a set of local execution steps. And these can be data parallel. They can use something like Spark or Hadoop MapReduce or some other efficient local computation framework. And then finally, a minimal, as much as possible, secure multi-party computation that eventually produces then a result. And Conclave also manages the full execution of this query. So the user experience is really very much like writing a query against in Spark SQL and running it against a Spark cluster, or perhaps running a query against a database, modulo some minor additions, which I will show you now. So this is an example of a Conclave query. And so far, this is basically the same query specification that a user would write if they were using a database that just contained all the data from all the parties pooled in one place. And specifically here, we are trying to compute our average credit score grouped by the zip code demographic information. And these operations, you see projections, aggregations, joins, and then finally writing the output. This syntax is very familiar to data analysts because it's very similar to Spark SQL or Dryad Link or other frameworks that people already use for clear text computation. Now, specifically note that here the bank's information is actually treated as a single collection, even though ultimately it actually ends up coming from different parties, and we're going to be doing MPC over it. So, of course, we can't just run this. Conclave does need a little bit more information from the programmer, and we try to really think hard about what information is intuitive for people to provide. Specifically, what the programmer needs to provide is information about who the parties are and where their endpoints are running. That makes sense. And then the programmer needs to specify the schema of the input. Now, of course, you always have to specify the schema of an input to a relational computation like this. But Conclave adds some very selective annotations that make it possible for our query compiler to insert the MPC operations where necessary. And specifically, we need to identify at which parties each collection exists. So in the case here, the demographic exists at party A, which is the regulator, and the the credit score information exists at parties B and C. So it is a distributed collection over parties B and C. And finally, the result gets sent to the regulator. It could be sent to multiple parties too. So this is the user interface. Now let's get onto the automated analysis. So what Conclave does is it starts out by basically modeling the whole computation as one giant MPC. And then it sort of tries to claw it back and reduce the amount of work that happens under MPC. So one observation that the rules in our query optimizer make, well, there's a concatenation here that combines the two banks' information into the single relation that then the query is expressed over. But we can actually distribute the operator that happens below that concatenation, namely the project operator, to the two parties and do it above the concatenation. So Conclave's query optimizer will rewrite the computation like this. And now we're at a point where we can actually do that projection locally, execute it at the parties, because it's running purely on local data. And there are other such rewrite rules that keep pushing effectively the frontier, the MPC frontier, where we enter MPC further and further down the computation. Now, finally, we can also push up the bottom of the computation through reversible operations, such as order, sort operations of a set of records that get revealed anyway, because that is something that the client could do no matter what. Unless the sort order was particularly secret. But in this case, let's say it's just sorting by zip code, and the fact that the zip codes exist will get revealed no matter what. So there is still a problem here, because the join and the average, which are the two operators that we saw being really, really expensive early on, are still happening on the MPC. So this is where our hybrid protocols come in. And I'll run you through an example of the hybrid join, and then in the paper, we also describe other hybrid protocols. So a join under MPC is very costly because in many implementations, we have to do order n squared non-linear operations under MPC. So this is those kind of network operations where multiplication requires communication across the network. And the observation that Conclave makes is that, well, there are some pre-existing trust relationships between these parties that we can exploit. Now, that is trust relationships that are specific to subsets of the data. It's not trust for the whole data, so there are no trusted parties here. There's just the idea that for specific columns, such as the social security numbers here, we might have a trust relationship. The banks might be happy to reveal to the regulator that a specific social security number has an account with them, but they do not want to reveal balances or credit scores or other private information. So in the Conclave program, the data analyst can just add this little extra optional annotation saying, I trust party A with this column. And then the Conclave query optimizer will be able to do things with that information. Now, of course, every party also trusts itself with all its columns. So we've now established that the SSN column here is actually a column that everybody trusts party A, namely the regulator, with. And we call this kind of party a selectively trusted party. So specifically, the party is trusted just with the SSN column and with nothing else. And in that situation, Conclave's rewrite rules will now insert this hybrid join protocol, which is much more efficient to execute. And specifically, the hybrid join reveals the selected column here, that's the SSN column, to the party that has been identified as a selectively trusted party. And the other piece of information that's leaked here is the size of the result of the hybrid join. And that will be leaked to all parties. Now, if that is something that should not be leaked, then Conclave cannot apply this optimization, and then the parties need to not annotate in this way. Conclave can, of course, interactively inform parties about what information is going to get leaked after it's applied its query rewrite rules. And nothing extra is revealed. In particular, the secretive score column and the demographic information that exists at the regulator, which are not annotated with trust sets, are not revealed to anybody at all. All right, so let's see how we're doing. There's my mouse. Not here. Ah, there we go. I saw it there. There we go. Okay, so since I have limited time and I want to make sure that we get to see everything, I'll background the explanation of the detailed hybrid join protocol, and I'm happy to chat to you about that offline, but move on instead to the evaluation and show you some results of Conclave. And if we do have time, we can dive into the details. So in particular, the hybrid protocols that I just described to you, we implemented for joins, also for aggregations, and for another kind of join, which is a join on a public key column, which we call a public join. And Conclave automatically derives authorizations from these trust annotations that I showed you on the input schema columns for intermediate columns, and then decides whether it can use such a hybrid protocol. In particular, the intuition that I would like you to think about here is, if a party can derive a column that will be revealed by one of those, hybrid operators to a selectively trusted party, then if a party can derive that column from annotated input columns, then it can act as a selectively trusted party over that column. And in our paper, we have simulation-based security proofs that prove the correctness of these protocols, the security of these protocols. We assume correctness and we prove security. Implementation-wise, this is a link-style relational front-end. I showed you a bunch of programs already. We have rewrite rules on the graph of operators. We generate code for Spark and the ShareMind and Oblivious C MPC front backends. And this is all about 8,000 lines of Python. Now, in the evaluation, I'll show you results for runtime on some realistic queries as the data size grows, and the input on performance that Conclave's trust annotations and hybrid operators have, and then compare to SMSQL, which is another state-of-the-art privacy-aware query processor. And we're going to run with 3 parties, running each a free virtual machine Spark cluster and ShareMind as the MPC backend. So the first query is the one you've already seen, the average credit score by demographic. And if we run this with ShareMind only, the full computation now, not just an individual operator as before, we end up with this curve. If we run it with Conclave, and again, less is better on the y-axis, we run it with Conclave, we get this curve. which, given that the x-axis is a log scale, actually amounts to 2 orders of magnitude better scaling, or scaling to 2 orders of magnitude larger input data. The reason here is this query is very amenable to the hybrid protocols that I described to you. In particular, it can use both a hybrid join and a hybrid aggregation, which both reduce the amount of work that happens under MPC by having a selectively trusted party catalyze the computation. Now, this idea also applies to other queries. In particular, we looked at a query that the SM-SQL paper authors looked at, which computes the count of patients who've been diagnosed with a specific sickness and been prescribed aspirin across multiple hospitals. And again, what we find is that Conclave increases scalability by 2 orders of magnitude over what SM-SQL on its own can do. And I should say here, we manually implemented some of the optimizations that SM-SQL does, which are orthogonal to the ones that Conclave does. So you could combine the optimizations in a single system. So again, the win here is because there's a public join happening. There's a join on a column that's actually the patient ID column that's actually public to everybody. And we reveal that to a selectively trusted party, but hide all the secret data. And then finally, we ran a query computing the market concentration in the New York City taxi cab market, computing something called the Herfindahl-Hirschman index, which is basically a sum of squared market shares divided by the number of companies, I believe. And the data here gets really quite large. So we go up to 1 billion records, which are millions and millions of taxi trips in New York City. And we find that, again, Conclave outscales just running this computation completely and ShareMind by several orders of magnitude. In this case, it's 6 orders of magnitude. And the reason here is that Conclave manages to push the frontier of the secure multi-party computation sufficiently far down to really reduce the amount of data before we enter MPC. And this happens automatically without the programmer needing to be aware of it or specifying it. So to summarize the evaluation, Conclave scales to orders of magnitude larger data, larger input data than pure MPC, and it nevertheless exposes a high-level relational query interface that's familiar to users already and outperforms prior MPC-aware query compilers like SM-SQL. And there's some other related work. Wisteria specifically is a system that also allows mixed mode computation where some is in clear text, some is under MPC, but users have to write programs for Wisteria in a custom domain-specific language, so it's much less usable than Conclave's relational front end, but of course allows more fine-grained optimization. And then SM-SQL, I already mentioned. There's also Opaque, which is a recent systems paper that relies on trusted hardware using SGX for this kind of private computation. So to summarize, Conclave is a query compiler for secure MPC on big data, automatically shrinks the MPC as much as possible, and we have new hybrid protocols that combine MPC and clear text computation for specific optional trust annotations that really speed up operations like joins and aggregations. And Conclave scales to orders of magnitude larger inputs than just running pure MPC. Our paper will appear at Eurosys in late March, and if you want to have a look at the preprint, I'm very happy to share it. And our system is also open source on GitHub. Thank you very much. All right, questions?
In your example, could the banks decide individually whether to trust the auditor with their SSNs? They don't, or do they all need to agree to a trust?
So everybody agrees on the program, the input, including the schema specification. But banks can decide which trust annotations they authorize on the specific line in the input schema that corresponds to their data. Now, there's no enforcement mechanism in Conclave for this. This would require out-of-band communication for them to agree that everybody is happy with PA being put into this annotation before we execute the computation. But of course, Conclave does show the query to everybody before it executes it, so they can deny participation if there are trust annotations in there that they didn't authorize.
Okay.
2 questions. One, how much time does the query compilation take?
Milliseconds.
Okay. And your motivating example would seem to scale up not just to large data, but also multiple banks.
Yes. So sorry, was that the end of your question? Is there more?
How do you scale up the multiple parties?
Yeah, so our focus in this work has been the size of the input data rather than the number of parties. So unlike other existing work in secure multi-party computation on scaling to thousands or hundreds of thousands of individuals who have data on their smartphones, perhaps, we're assuming a relatively small and fixed number of parties here. So you would think of 3, 4, 5, and specifically the backends that we're using, specifically ShareMind is restricted to 3 parties. I believe C is sort of in the naive way of using it restricted to 2. We also have VIF, a very rudimentary support for VIF, the VIF front backend, which supports any number of parties, but is much slower than the other one. So in principle, yes, you can scale to many parties, but that's not so much the objective of the work. So the query rewrite rules are all about reducing the amount of data processed under MPC rather than efficiently scaling out to many parties. So that would be complementary work in the future. All right, thank you.